Um, we did this example in the previous video, but then we only were finding the mean square value, not the whole autocorrelation function. Now let's do this same example of the system and its input, but now we'll find the autocorrelation function. This will be another example of evaluating integrals involving the Dirac delta function, impulses. So it's that same first ordered system with white noise of amplitude A as the input. The weighting function of this transfer function is this. I think we found that out before. The autocorrelation function of noise, of white noise, is the Dirac delta function. So here's our formula for the autocorrelation function. Here it is in this case. It's the weighting function G, the two different arguments U and V, times A times the Dirac delta function, this argument. So here's the double integral we need to take. And I could take it either way, either order, UV or VU. And remember, I have to change the limits of integration. You have to go along with the variables of integration. U is associated with T1, V is associated with T2. So I can use either one of these formulations to evaluate the integral. And we want to know which one do we want to use. We go through the same kind of logic we did with that Wiener process case. We want to look at the two cases where T2 is greater than T1 and where it's less than T1. In this case, we want to integrate over V first, up this way. That way we don't have to figure out this point and divide it up into two different regions of integration. And we don't have to worry about going outside limits. Integrate over V first, we're okay. So then we want to we'll use this case. So we use this for this case, right? That's what this is. And let's see. What V makes this argument 0? Well, that's where V equals U plus T2 minus T1. So substitute that in for this V. And I would get that in that argument. And the rest of this thing, well, that inner integral then goes away. You know, this is the result of that inner integral of what's in here. So now we just need to integrate over U. And let's see, we can pull out the T2 minus T1 because it doesn't involve U. You're left with the 2U in here. You can take this integral easy enough. And here's the kind of ugly result. Now we'll do for this picture on the right, we're going to integrate over U first. We're going to be using this formulation here. So now we want to substitute in the U, what makes this argument 0. That's where U equals V minus T2 plus T1. So we make that substitution in for the U. V minus T2 plus T1 plus V. And that's what the inner integral evaluates to. Now we just do the outer integral. Pull out the T2 minus T1 again. And we're left with this guy. You can take that. Anyway, here's what you end up with. So we have different answers for the different regions, or we could combine them. This one way to combine them is this way, to capture both cases. It's this where this T tilde is the minimum of the two times. And just out of curiosity, what happens as that minimum time goes to infinity? Infinity. Get this? That goes to 0, and you're just left with 1 here, so you're just left with that, which is this. How is the difference between the two times? Oh yeah, that means the mean square becomes this, which we found before. Well, let's see. In this case, the output is stationary in steady state. See that the pole is -1/t, which is strictly in the left half plane. So this guy is a stable system, and you do get a steady state constant as an answer. So if your only interest was in steady state, you could have found the answer using steady state analysis, stationary analysis. One more example, not in this video, and that will end this whole module on random processes going through linear systems.